So in this video, we're going to be revisiting some code from our previous videos, and I have it pulled up here. We plotted some isotherm curves on pressure and volume with our given temperature. We came up with a function for a specific volume here using Cardano's formula and the cubic polynomial equation of state. So we're going to be using this information that we've already come up with here to plot a superimposed two-phase envelope onto our isotherm chart here. So to be able to understand what that means, we're going to be looking at the Maxwell construction. Maxwell was a man that came up with this idea that if we have a pressure volume diagram of some substance, the area underneath this curve, our isotherm curve, and some pressure should be equal to the area above the curve between the same pressure here. And if you notice, if you're able to recognize, there's 3 volumes here where this happens that we're looking at. Those are actually going to be our specific volumes that we found in the last video. So this is going to be extremely important to understand so we can use this idea throughout our coding. So another important thing that I wanted to mention is that if we look at our isotherm curves here in our standard PV diagram, you can see that below our critical point, we have this envelope here where we have a constant pressure. So that's basically what we're going to be looking for in our chart here. So that's what we're going to be making, is that constant pressure line in there. So to do this, we are going to be using the quad function from SciPy, and this is going to allow us to be able to take the area underneath the line of the curve like we had over here. It'll allow us to take the area in this space and the area over here. So to do that, we need to define it. We'll call it our cubic, I'm sorry, not cubic. We want to define it as our area using quad. And what we're going to need to input to make this happen is our pressure and temperature. So when we think about our Maxwell construction here, we know that we're going to need to use our bounds of integration. So that's going to be our V1, V2, and V3. So we already know those, we found those in this function up here, so we can bring that down. And we want to unpack that and define what variables we want those to output as. So we'll call it V1, V2, and V3. So next we need to actually do the integration part. So we want to define a function of our integrand. And what we're going to input for that is going to be our volumes. So we'll say V. So with this function, we want it to be returning basically this equation here. So our P minus PEQ. So P will just leave as P. So we'll start with return P. And our PEQ is going to be the same as our calculated cubic pressure up here. So we'll bring that down also. So now we want to make a return statement for our area quad function. So we'll say return. And this is going to be where we use the quad function. So the cool thing about the quad function is that if we just input our function here, and then A and B are going to be our lower and upper bounds. So it's going to actually take the integral given our function and bounds and do that calculation for us, so we don't have to do any math here. It'll do it all for us. So our function here is going to be integrand. Our lower bounds is v1 and upper bounds v2, and that's just saying, like, it'll take the area of this first space here, and then we're going to need to include another one where we take the area over here. So we'll have quad integrand v2 this time as our lower bound and v3 as our upper bound. And normally this will work out just fine, but it's going to give us our answer to this integral here, and it's also going to give us an error approximation value, but we're not too worried about that. So to get rid of that, I'm going to include 0 just to indicate that it's not a tuple and we don't need that. So it'll just give us our answers. And looks good. So remember, we are trying to look for a pressure value such that our areas here underneath and above will be equal to each other. So to be able to get at that pressure value, we need to use the root solver. But to use the root solver, we need to define some function for it to call upon. So we're going to define a new function, and we'll call it the sum of the areas. And when we use the root solver, it's expecting us to put in some kind of vector, so we'll just call it vec for now. And then we're also going to need to call upon t, since in our area quad up here, we're calling on t also, so we'll need to bring that in also. And we can go ahead and say that our pressure is going to be our first index of our vector. So we'll say vec 0. Oops. Yes. All right, and then we're going to need to bring in this area function here. Because that's already calculated our volume, or our areas for those integrals. So we can go ahead and unpack that and call it our left and our right areas. So now I think we're ready to make our return statement, and that's just going to be our left plus our right. And since one of those is going to be negative, it should give us a value really close to 0 when we input our temperature. So now we're ready to go ahead and use our root solver. So we'll do root, and then we need to call in the function we just made. So we'll say sum areas, and we need to provide our vector here, this vector, and we specified that it's pressure, so we can go ahead and pick some specific pressure that we want to use, which we can just do 1 atmosphere, which is going to be 101.325 pascals. And then we also need to say that our argument, I guess, args is what they call it, is equal to temperature. And basically, whoa, what just happened? All right, try again. 101.325 pascals. Args equals T. All right, so that args thing here is saying, like, okay, we've supplied our vector here as the pressure, and we're just saying that's the other input or argument that we're going to need in this root solver. So now that we have that, we're going to need to pick some value for our temperature. So we'll just say T equals 400 for now. And then if we go ahead and do that, we have an error. Uh-oh. Okay, so I figured out I hadn't ran this part up here, so it wasn't taking root into our code. So I reran everything and it looks good. We have this array down here of 90884, and that's actually going to be our pressure with this specific temperature here. So as you can see here, for boiling point of water, this 373.15 here for the temperature, the pressure is going to be 90884, which is pretty close to what it should be. So this was just our way of checking to make sure that this root function works. So we can go ahead and define it, and we'll call it pvap. And we can do the .x to just call upon this array down here. And then we can also specify that there's just one value here in the vector, so we'll say 0 and put pvap here, and you can see we just have our pressure there. So the next thing that we're going to want to do is actually change this to just be some temperature, and we can put it up here actually, 373. So next what we're going to want to do is bring in our cubic volume, so the specific volumes that we found in our last video. So, oops. Bring that into here. We can actually unpack that. So if you remember, our specific volumes were the volume of our liquid, intermediate volume, and volume of gas. So we can name them volume of liquid, volume intermediate, and volume of a gas. So since our intermediate volume is kind of irrelevant, it's not an actual thing that we would find in real life, we can just replace that with an underscore so that if anyone were to see this code, they would know that we're not dealing with that intermediate volume. So now we want to plot our two-phase envelope, and to do that we need a list of values. So we're going to store our liquid volume, so our VL. We're going to store them as lists. And we also need one for our gas. And we're also going to need one more list, but that's actually going to be our pvap here, the root that we made. So now looking at temperature, if you remember from our chart up here, we used many different temperatures to get those many different curves, and we want to be able to do that again. So instead of using this specified value for temperature, we are going to make a for loop. So for our temperature, and we'll just say, since we're going to be plotting, we'll do linspace for now. And we can go ahead and use, I think, the same values that we used up here, 250, 775, and 25. 50. All right, and then we're going to want to bring in these into our loop. We're actually going to want to bring in our pvap list, and we want to do dot append of pvap, and doing the dot append is just going to say that every time we go through our for loop, we want to include a different value for pressure. Alright, so I noticed a couple errors here. So this 1e to the 7th, we need to change that. We need it to be our vapor pressure here. So that was my mistake. And then also we want that to just be temperature. And I'm going to make all these t's the same, just to make it easier. And then our lens space needs to have numpy in front of it. And I'm also going to go ahead and change these to up to 500 and then only do 10, just to hopefully make it a little simpler. So now we can keep going here. So with our PVAP list append, we also want to bring in our liquid volume list append with our BL, and the same with our gas. Okay, so if we look up here at our root, we had supplied a guess for our pressure, the initial pressure to start at. So we can actually go ahead and change this to just say guess, and then define it up here with some initial guess. And since we're starting at 250, we wanted to pick something a little bit lower than that. So I'm just gonna say 1,000 pascals. And then we can actually bring that into our loop. And by doing this, every time our for loop runs, it's going to be inputting, I'm sorry, our guess is not going to equal 1,000. It's going to equal our PVAP. So that way, every time it runs through, it's going to take our guess from the last run and include it in the new run. So hopefully that'll be a little more accurate than just guessing a number each time. All right, so we're just going to run through this, make sure it works. It all looks good. And we can actually test our volumes for liquid just to make sure we have everything correct. And you see here we have changing volumes, which is really good. That's what we want. That's how we know our loop is working. Everything's good. So now we're ready to plot it out. So I'm just going to copy all of this. And paste it down here. Alright, so the first thing we want to do is make this Fig 2. Change the name of that. And up here. Alright, so let's see here. For our x-axis, we want to change the range because where it's at right now is going to be way too large. So let's see, we could do, oh, we need to say range first. Let me log base 10. And we want the minimum value of v. And then let's do something like 10 to the negative second. We'll see if that works out. Alright, let's see, parentheses. Alright, I think that should be good. And then for our scatter plot, we're going to leave that in our for loop and just make another one because we're going to need that to display all of the lines that we had already made, all those isotherms. So we're going to need 2 of these actually, one for our liquid and one for our vapor. So instead of V, we're going to have volume of our liquid, the list. And instead of pressure, we're going to have the PVAP from our loop from up here. And then, let's see, the name, we want it to be, we'll call it liquid phase. Alright. And then we can do line color, just so it's like really evident which line we're looking at. Alright, so now we can go down here, do the same thing for our gas. Call this the, we'll say vapor phase, not gas. All right, let's see if there's anything else that we might need. I'm gonna make this a little bit smaller, or maybe this one too. Uh-oh. My issue, I forgot to make this list. Because we want to bring in the list of those values, not just one value. I'm not sure. Oh, forgot to put list on the gas too. Alright, hopefully that's good now. Let's bring it down a little bit. It seems a little too low. So the first issue I can see here is that you can tell our lines are not connecting. So we can fix that actually. So if we go back, let's see if I have it, we can see there's a nice smooth curve here, and as our volume is increasing when it's a liquid, our pressure is increasing. But when we get to the gaseous phase over here, the vapor phase, our pressure is decreasing when volume's increasing. So we need to account for that in our code here. So what we can do to do that, we can just add our liquid volume plus our gas volume. So we'll do our volume of our liquid list plus our volume vapor, and we can call this our V plot, so it's our new plot with our combined volumes. And then since one is going from positive to negative, there's a way we can account for that in Python, and it is just like this. And you can find that in W3 schools and tutorials on how to use Python and lists. So we need to do the same thing again for the y-axis. So that's going to be our, we'll call it our p plot. That's going to be our p vapor list plus another one. And again, we're going to use this syntax. All right, so if we run that out, it's good. Now we're going to need to change it in our plotting code down here. So our x is now going to be our v plot, and our y is going to be the p plot. And I'm going to go ahead and get rid of this second one now. We don't need that anymore. We can change the name. Instead of liquid phase, this was our two-phase envelope, remember? Oh my goodness, can't spell. Envelope, there we go. And if we look at that, see, it's much better. We have this straight line here. They're connected. Can zoom in and see that. The big issue that we can see though still is that it's a straight line, and we want to have this nice smooth curve here. So to be able to get this black line here of our volumes to be a nice good curve like from here, if we think about what we have here, so we have our temperatures as linearly spaced. So that makes me think they might not be linearly spaced, and we might need to make them either like some kind of ln or exponential. So if we pull up Desmos here, we can actually graph some things to play around and see what we might need to change it to. So if we just have some kind of graph of x, for example, that's what it's going to look like. If we make, let's see, I think you have graphs that have curves to them. We can have ln of x. That one's alright, not too bad. Let's try another one just to see. Well, that one's pretty good, but it's kind of going the wrong way because we want this to be like that, but it's just kind of flipped-flopped a little bit. So we could try negative of both, and that's really what we want. And if we do 1 minus that, it'll bring it up to our 0, 0 point here, and then we can manipulate that to start at our initial temperature of 250. So then if we zoom out, oops, zooming in, zoom out, all right. So we can see we have a nice curve here, and we need to shift it to the right a bit also. So we would have our critical temperature minus our 250. So I'm just going to pick a number and say 700 minus our 250. Not sure what the critical temperature for water is. I just picked a random number. Alright, so if we come up here, doesn't look good from very far away, but if we zoom in, we can see it does have that nice curve that we're looking for. Yeah, just like that. So if we go back, we can actually change our temperature to terms of x, so we can manipulate that to become exponentially, to become an exponential. So we can leave that at 250. Actually, since we are going to add 250, we should set it to 0. And instead of 500, that's going to be way too big, so we can go to 10 maybe. And we're going to want a lot more points so we can get that nice curve and we don't have any straight lines. So we can just bring it all the way up to 500. Okay. Let's see, do we need to change anything else? Oh yes, we need to make our temperature now. So temperature is now going to be, we're going to bring in our critical temperature minus the 250. That's going to be multiplied by 1 minus our e exponential of negative x. Then we want to subtract that whole thing from 250. So that should be good. Let's see. Alright, so I'm thinking what the issue here is that our temperature is too big because that's going to be, because that'll give us way too high of a temperature when we plug this into the equation. So if we bring that down a bit, how about like 8? That'd be good. Still too high. Let's see. 7. Still no. Let's see, where's our issue? Alright, so I found my error here. I did minus 250. It should have been plus 250 in that equation for temperature. So now we can go ahead and plot that again and see if we zoom in. We can see we have a nice curve, much nicer than what it was before. So hopefully this showed you guys a little bit more about how to make that two-phase envelope for our isotherm PV diagram.